we have to use some eigenvalues. We have to use some Schrodinger's method, Schrodinger wave function, and all the methods we will apply in this chapter. Okay, so the chapter name is 1 and 3 dimensional energy eigenvalue problems. So we will first discuss about one dimension, and then we will expand that to the 3 dimensional problems. Okay, so what is energy eigenvalue problems? We discussed that there is eigenvalue equation which satisfy when operator is operated on the wave function, and we get some eigenvalue into again that same wave function. So this part of the eigenvalue equation we have to solve for different cases. So you can see here there is a square well potential with rigid walls and finite walls. So I will tell what is the difference between these two. And this chapter is very important by the point of view of net gate set exam, or whatever, just TIF or any exam you give in physics. There is at least one question on energy eigenvalue problem. Okay, if you know in 1 dimension, then it is easier to extend that in 3 dimensions. Okay, so we will first discuss what is 1 dimensional energy eigenvalue problem. So we will first discuss the square well potential. Now here there are two different kinds of things they have given, rigid walls and finite wall. So I will give the difference between these two. So rigid walls, or this is also called as a impenetrable wall. So this means we cannot penetrate the wall. What is penetration? To pass through, to go through the wall. Okay, so therefore it is called as rigid wall, or finite wall is called as a penetrable wall. So we can penetrate through that wall, or we can pass through the wall. V means the quantum particles can pass through, or like there is a finite wall. This is also called as a infinite wall, or infinite square well. Infinite well. Finite wall they are calling, or well calling. Okay, anyway, so we generally call this as a well, finite square well or finite well. So what is difference between wall and well? So what I am talking about this kind of shape. Okay, so these are walls, and these walls make this well. Well means vihir. Okay, so same case is there. So well also has some walls. So they are talking about this wall. So rigid walls means this wall is so high, it has infinite distance or infinite height, so that the particle, if the particle is in the well, it cannot go outside. So that's why I am calling this as a impenetrable. Okay, so this goes to infinity. So this never ends like this. Okay, on both sides. So this is called as a rigid or rigid wall or impenetrable wall, or the well is called as an infinite well. Finite wall. Okay, in finite wall what happens? There is finite distance. Okay, only this is the height of the well. So whatever we are talking about, this is called as a potential well. So this graph is about the potential energy versus distance. Vertical axis is potential energy, we denote it as a U or V, and horizontal axis is we will denote by X. Okay, X or R, but we are talking about 1 dimension, so it is easier to use X. Okay, now in your book there is only one problem is given. The symmetric type of problem is given for both cases, infinite and finite cases. But I will tell you both cases because in NET exam they might ask in different way. So you should know what is the case. And this is one of my favorite case. Okay, this 1 dimensional eigenvalue problems, square well potential, is one of my favorite and one of easy topics in the quantum mechanics. In last chapter there are some concepts which are difficult to consume or to adapt or to understand, but this is very easy, and if you know the basic conditions on wave function, then you can solve this very easily. Okay, so we will directly start to solve the infinite well. What we have to do, we have to solve means we have to find out the wave function of if the particle is in this infinite square well or rectangular well. We call it as a rectangular well also. So what is the wave function of this particle, or there can be number of particles here and there in the well. So what are the possible eigenvalues of energy we have to find out. Therefore the name of the topic is energy eigenvalue problem. So you will find out the wave function, and then you will find out the energy values of each different states. I will also tell you in two different ways how to solve this. In your book there is only one method, that is symmetric well. Okay, I will draw. Okay, so let's say this is infinite well. So on the same diagram I will show you the two different methods. Okay, so what two different methods? This potential outside the well is going to infinity anyway. Okay, so this is not changing in both cases. What is changing is how we label the distance axis. So as I told, this is x axis or r axis, whatever you can name this. So I will write this with a different color so I can show you the distinction. So in your book you can see this, there is a origin at the center of the well. Therefore I can name this this part as a minus a and plus a. Okay, so this is minus a or this is plus a, or in some cases this is called a symmetric potential. Okay, because on the left hand side and on the right hand side of the origin the potential is symmetric. Up to a this is zero potential, so inside there is no potential. Okay, so inside of the well there is zero potential, and outside it is infinity. Okay, outside anywhere else, but outside the minus a and plus a, the potential is infinity. And what about the asymmetric way? So I will define here the origin, and therefore here it will be a and here it will be 2a. Okay, so anyway the width of the well is 2a, total width from this point to this point. This width is 2a, but there are two different notations or two different ways to approach the problem. When you define this in this way, this is very easier to solve. Okay, here is you have to impose more conditions for symmetric well. So I will first you explain the asymmetric case, and then we will go to the symmetric case which is in your book. Okay, so we have to solve the Schrodinger's time dependent or time independent equation. So what we can do, we will consider that the wave function or the potential, why it is dependent or independent, that depends on the potential energy. So inside the potential is 0, outside it is infinity, and it does not change with time, right? Therefore we can use the time independent Schrodinger's equation, minus h cross square upon 2m. So this is kinetic energy operator, and we are writing in one dimension only. So I will also write the second derivative, d square upon dx square, which will operate on the wave function psi, right, plus v psi. So v was the potential energy. This is equal to in time independent part, kinetic energy plus potential energy is constant, so therefore total energy is also constant. So we don't take IH cross dabba by dabba t, we take the eigenvalue E, or sometimes we also write it as H, which is representing the Hamiltonian. Okay, so this is our equation, Schrodinger's equation, time independent equation. So we have to use this equation. Now if we are going for the second approach, in the blue color what I have written, if we are going for this approach, symmetric well, asymmetric well, then what will be the wave function, and for symmetric case what will be the wave function? So we are going to see, but in general the wave function for both the cases is same. Okay, how can I say this? Okay, so outside this well, the potential is infinity, so there is no possibility of particle finding outside the well. So outside the well there is no wave function. Okay, so what we have to do, we have to find out the wave function only inside the well. Now inside the well you can see the potential energy or potential is equal to 0. So this part of the Schrodinger's wave Schrodinger's equation is equal to 0. So we don't have to worry about this. We only have to solve this equation. Now you can see this is differential equation of second order. Let's say y double dash plus k square y. So if this is our wave function, differential equation, then the solution, general solution, this is mathematical part. So this solution for this is a sin kx plus b cos kx. So this is general solution for this type of equation. So instead of k, we will also write this equation also. Okay, try to write the equation in this form. What I will do, I will take e side to this side. There is minus sign on both equation, there will be. So I will multiply by -1. So here it is anyway 0. So all equation I can write in positive sign. Then I will multiply the whole equation by 2m upon h cross square. So this same equation will become psi is there as it is. So what I have done, I have taken this e to another side, or let's assume that this negative part is I am taking to this side. So here it will be 0. So h cross square by 2m d2 psi by dx square plus e psi is equal to 0. So I am multiplying by 2m by h cross square. So here it will get cancelled, and here it will be 2me upon h cross square. So this is nothing but the differential equation we have to solve. So here it was k square. So we will define that k square is equal to this part. Okay, so you can equate these two equations. Instead of y, we have psi as a function, and instead of this k square, we have 2me upon h cross square. Okay, so from this, what I can write the value for k. K is equal to under root this part, right? Because this k square is equal to 2me upon h cross square. So I will write this in the square root 2me upon h cross square, or I will take this outside the bracket, h cross. Okay, so this is my k. So up to this part, this is same for both cases, for symmetric case as well as asymmetric case. Okay, because we are not imposed any conditions on this. So this is my general solution. Okay, now where the difference will be? The difference will be when we are applying the boundary values. So what is boundary value? So when we solve on differential condition or differential equation, we put some condition to find out this constant. A and B are two constants here, or we can use C1, C2. In mathematics, you write C1, C2. We have just here used A and B. So to find out the values of A and B, we put some conditions on the wave function. I have to apply conditions to get the value of A and B, so that I can get what is the exact wave function in that square well. In asymmetric well, what I have done, here it is 0 and here it is 2a. And what we will do, we will use the fact that the wave function outside is equal to 0. Wave function psi is equal to 0 outside, because there is no possibility of particle finding outside, because this is infinite square well. Therefore, here the wave function is equal to 0. I will draw with a different color now. Here the wave function is equal to 0. here it is 0. This part is only inside this part. Okay, now we have the condition for true wave function, that wave function must be continuous, right? Wave function must be continuous. So continuous means at every point it will have the same value. So if I am traveling from left side to right side, in this side if I am traveling, I am getting the value 0 at this point. So it should not suddenly jump to any other value. So it should be 0 at x equal to 0. So even if I am traveling from this side, at this point the value should be the same as this. So here it is 0. So this must be 0 at x equal to 0. Okay. So what condition I am getting? The wave function psi is equal to 0 when x is equal to 0. This is my first condition. I am applying first boundary condition. Okay. So put this in this equation. Let's say this is equation number 1. So sine 0 will become 0. So this part is going to be cancelled. And psi is anyway 0. So when you put cos 0 is 1. So b is equal to 0. So from this part you get b is equal to 0. This means this part of the wave function is absent. So I am getting only a sin kx part. Okay. Now I will apply another condition. Okay, because this well has two boundaries. One is at this point x equal to 0 and another is at x equal to 2a. So outside the same analogy we will use here. Okay. So as I am coming from here or I am coming from here, the answer should be the same at x equal to 2a. Outside it is 0. So it should not jump directly to some other value. So it should be 0 at this point also. So I get another condition. Psi is equal to 0 if x is equal to 2a. Okay. So this is my another condition. Put this value in this equation. So I will get 0 is equal to a sin kx. Okay. K into 2a. Instead of x we put 2a. Now there can be two possible conditions. This has to be equal to 0. First condition, that a must be equal to 0. If a is equal to 0, then the whole wave function is 0. So inside also there is no wave function. So this has no meaning. So a cannot be 0. So what can be 0? Sine part must be equal to 0. And this part is not 0. 2a is not 0. K is not 0. So there must be some other values. Tell me when sine function is 0. It is 0 at various points. It is 0 at this point. It is 0 at this point. It is 0 at this point. So what are these points? N pi. Okay. So this is pi by 2. This is pi. This is 3 pi by 2. This is 2 pi. Okay. This is 5 pi by 2. 3 pi. So at pi or 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, the value of sine function becomes 0. So what we will do, if this is 2n pi, okay, what I will write, this is 2n pi, not 2n pi, just n pi, any n pi. So this must be equal to 2a into k, this 2a into k. Then only this function can become 0. So I will write the condition 2a k is equal to what? N pi. Or take 2a to this side. So I will get value of k. K is equal to n pi upon 2a. Now compare this with the previous definition of k. This definition. Okay. Under root 2me upon h cross. So this is equal to under root 2me upon h cross. Previously I have written this outside, so I haven't written square, but I have to now write the square. Okay. So what is the whole purpose of doing this is to find out the energy value. So we have to find out the energy value. So what we will do, we will square on both sides, and then we will take h cross square by 2m to another side. So what will be the value of E? Now here the value of E depends only on A, n, right? M is constant, h cross is constant, A for this well is also constant. So we will write this E n. So this becomes n squared pi square upon 4a square h cross square upon 2m. So remember, h cross square pi square upon 2m. This is common for each wave functions. Okay. So in h cross there is h upon 2 pi. So if you have to write in h part, the pi square can get cancelled. So extra part will be there. Now because we have taken this 2a, here we are getting 4. Okay, 2 square is 4. But if it's just a, this 4 will not be there. Okay, or if I say this is L, so this is equal to L square. So what is the value of energy? Okay, I will write this in L square h cross square pi square n square. You can write this in any sequence because these are just constants or numbers upon 2m L squared. Okay, so what is L? L is the width of this potential well, okay, which is 2a. So you can put the values of L, okay, whatever it can be. It will change from problem to problem. If in some case you have given it is a, then this 4 factor will not be there. Okay, if in some case you have given some value, let's say 100, then accordingly the value will be changed. When you solve problems in quantum mechanics, the wave functions are given or the conditions are given. Let's say for an electron in atom, there is a potential value of some angstrom, let's say 2 angstrom. So you have to put the value 2 angstrom or 3 angstrom, whatever the value given is. So that is our value of L. So this part is easier to solve when the asymmetric well is there. Okay, because this is 0, sine 0 becomes 0, and this part cos 0 is 1. So B has to be equal to 0 all over the space. And because B is 0, A cannot be 0. Therefore this part must be equal to 0. So therefore this is very easier to solve. But in your syllabus for MSc, you have the symmetric well. Okay, so we will also solve for a symmetric well. This is a symmetric type of well. Okay, now we have to discuss the symmetric. We are discussing infinite square well itself or infinite rectangular well itself. Okay, but by the different approach. Okay, so okay, we'll draw the well. So this is now 0 at the center. Okay, 0 is at the center, and so therefore here it is minus a, here it is plus a, or again I will write here L is equal to 2a. So the energy values, okay, energy value for each energy level does not change by this origin. If you shift origin, you can also write the origin at this point, right? This point, any point we can select as origin. The value of energy does not change. So why we do only with 2 ways? Because these are easier ways. Okay, so this is easy to solve. Again we have solved the equation, I mean general equation. We know this equation number 1 is general solution, a sin kx plus b cos kx. Again this same wave function is there, but what I have to do, I have to apply the boundary conditions. just like we did in the previous case. Okay, so what will be the case now? Here again the case is same. I mean, the value of wave function is 0 at this point, and it is also 0 at this point. Okay, so it should be 0 at this point and 0 at this point also. So I will put x equal to minus a and x equal to plus a. So at that point, so when x is equal to plus or minus a, okay, then psi becomes 0, right? So what I will do, I will put the both conditions, and let's see what we can get. Okay, so psi is equal to 0. This is equal to a sine of minus ka. Okay, because instead of instead of x I have written minus a, so that has become minus a, plus v cos minus ka. Okay, so instead of x I have written minus a. Now you know sine of minus x is minus sine x, so this will become minus a sine kx. Okay, plus cos, for cos it is same, cos is even function, so it is b cos kx, ka. Okay, so we have this condition. This is first condition, right? We have to write another condition. So in that case we just have plus a instead of minus a. So this will be again 0 is equal to, because for plus a also the wave function becomes 0. So this is a sine kx, sorry, ka plus b cos ka. These two conditions we are having. Now consider addition of these two. What will happen? This negative part and this positive part will get cancelled, and this two part will get added. So 2b cos ka is equal to 0. So we can divide by 2. So one condition we can get from addition. If I add these numbers, add these two equations, what I will get? I will get b cos ka is equal to 0, right? This one condition we can get. And if we subtract, okay, if I subtract these two equations, this minus and this minus will become plus, so this will be 2 sine k, and this two parts will get cancelled because of subtraction. Again we can divide by minus 2. So again what condition I can get? A sine ka is equal to 0. Now consider this is our wave function. So both cannot be 0 simultaneously, or if both has to be equal to 0, then we have to do something. If b is equal to 0, then a cannot be equal to 0, then sine k is equal to 0. Or if a is equal to 0, then b cannot be 0 and cos ka has to be equal to 0. Because if a and b both are 0, then whole wave function is equal to 0. But we know there is some wave function inside the well. So a and b cannot be equal to 0 at the same time. So there can be two possibilities here. First one, if a is equal to 0, then cos ka is equal to 0, b is equal to 0, then sin ka must be equal to 0. So this second condition you look familiar with the previous condition. Okay, so from this we can get the same energy value. Okay, we will equate this k is same because this part up to solution part, both part is same. Okay, so k is equal to under root 2me upon h cross square. So there is also n. So nth energy level we can find out by the same way. Okay, so you see here k is equal to n pi by 2a. Why n pi? because sine n pi is equal to 0. Therefore we again get the same part. Okay, so now we will discuss about this part. So when cos ka can be 0, cos 90, cos 270, that is pi by 2, 3 pi by 2, 5 pi by 2. So when there is n pi by 2, then only this ka becomes 0. Ka is equal to n pi by 2, or from sign condition we have ka is equal to n pi, right? Previously it was 2a here, okay, because we have taken full width. So from first condition we are getting this is for cos. Okay, so this cos means even function. Okay, cos is a even function and this is odd function. Okay, so for even part we are getting this, and for odd part we are getting this. You can put the value of k here. So k is what? Under root 2me upon h cross square. So I will directly use e from this is equal to h cross square by 2m will be there. Then we will have n square pi square upon 2 square means 4, and then this a squared. Okay, you can see this is the same as we have seen in earlier case. Okay, and now what we have here e is equal to h cross square by 2m, this part is same n square pi square. Now there is no 2, right? So 4 will not be there, and this a square. Okay, anyway, so the condition is the same for both cases. Energy condition is same. Actually here it should be also 4. I don't know why it is not getting. Okay, anyway, you just remember this thing. So we are getting this is equal to n square pi square h square upon 2 into 4 is 8 m a squared. Okay, so this is the same as we get in the previous case. Here also we get the same. The difference is that, so this even is not n, this is function, even function and odd function. Okay, so this comes from what? You see, when cos ka is equal to 0. So this is cos part, therefore I am saying that this part is equal to even function. This is even function. Okay, function is even, so even function means cos part is there, and this is odd function. Now the energy values are going to be the same. You don't have to worry about the energy values. Energy values will be the same as the previous case. Also we got this value. So what will be the case? For first case a was 0, so b cos kx will be the wave function, and other part is a sin kx is the wave function. Okay, so I will write wave functions. So psi n is equal to one condition is that b cos kx. Now we are not writing ka because this is in general wave function inside the will. Okay, so energy will be the same for these conditions. But for this, what happens if n is equal to 2? If n is equal to 2, then this 2 and this 2 will get cancelled, and this will be cos pi. So cos pi is not 0. So this n has to be odd to get this even function. Okay, this n has to be odd. This has to be odd, because if this is even, then 2 and 2 will get cancelled and this will become pi. So cos pi, this is part of cos. So cos pi will become 1, right? Cos pi, cos 2 pi, cos pi is -1, cos 2 pi is 1, but they are not 0. So this condition will not follow. Therefore, n has to be odd if we have to use this wave function or this part of wave function. So for this, n has to be equal to 1, 3, 5, 7 and so on. Okay, and all other cases we use this is equal to a sin kx, a sin kx. So for this we can use n is equal to 2, 4, 6, 8 and so on. Okay, now remember, in this case what is going to happen? When n is odd, the function is even. When n is even, function is odd. Okay, so if we have to draw, okay, I will not draw here, I will show you the drawings. You can see here is the origin 0, here is minus a, here is plus a. So when n is odd, the function is even. Why we are calling this even? Because from left of the origin and right of the origin, the function looks the same. Therefore this is even function. So this is cos function. This is sine because it is 0 at the origin and it is asymmetric. It is positive here, it is negative here. Again, for n equal to 3, which is odd, the function is even because it looks similar on both sides. It is just like mirror image. Okay, so again this is cos function. Therefore whenever we draw the energy level diagram for symmetric well, we have first function is cos function. So this is cos kx. Okay. So when you put the value of k, you can see here the value of k, here it is n pi by 2. So you can put the value of n pi by 2 here. Okay, so cos n something, so n is 1 here. Okay, for here n is equal to 1. So this is nothing but cos, n is 1 here, so cos pi x upon 2a. So where is 2a coming from? You can see in this also there is 1 upon a. Okay, so that is coming from here, and 2 is coming from this pi by 2 condition for cos. Now again the second wave function is sine. So negative in negative side. Okay. So this is not to the scale. So like this. Okay, so this is sine part. So it is 0 at the origin. This is our origin. So here it is sine kx. So here n is equal to 2. Okay, so when you again put the value, so sine k was n pi, right? So here you will get sine, here n is equal to 2. So it is 2 pi x upon 2a. So you can see 2 and 2 get cancelled, but I will write this as it is because this is n. So you have to change the n. Okay, and this will be constant. This part is going to be remain as it is in your wave function. What is changing? As n is changing, the cos sine part is changing, and this n is also changing. Here n was equal to 1, n is equal to 2. Again for n equal to 3, this part is like this. Okay, so it is symmetric, just like we have seen here, it is symmetric. So for this we have cos 3 pi x upon 2a. Okay, so for n is equal to 4, again we will get sine function. Okay, for n equal to 5, again we will get cos function. So when n is odd, we will get cos function. When n is even, we will get sine as a function. Why I was talking this is a little difficult, because if you solve using the asymmetric will, using this type of will, all wave functions are sine functions, so you don't have to worry about sine and cos. But the problem in this is we cannot define even and odd functions. So that is benefit in symmetric type of well. But here also you will get the same energy value, n square pi square h cross square upon 8 m a square. Okay, you are getting the same value. Here it will be the same, wave function is same, sine 2 pi x upon 2a upon 2a, but here it will be also sine. Okay, so all sine wave functions are there for the asymmetric type of well. So this is pi x upon 2a. Okay, therefore you can use any of this, but the problem or the topic of this discussion is that energy eigenvalue. So energy eigenvalue is going to remain same in both ways, either you use symmetric well or asymmetric well. So in your syllabus they have used this type of wave, symmetric kind of potential they have used. So I guess this is enough for today. We will discuss the finite well. Okay, so what will happen if the well becomes finite? So finite means here also there are two different approaches. In one way we can say that here it is potential is equal to 0 and outside potential is, let's say, v naught. V naught means there is some constant value. Or there is another approach is that outside the potential is 0 and inside it is minus v naught. We can use any of this approach because in classical mechanics also or in Newtonian mechanics also you have discussed that potential energy we can take any reference. Okay, we can use the zero potential at the surface of earth or at the center of earth. As long as the difference is same, we don't need to say what is the origin. So we can use any of these two approach. So we will go with the blue one. Okay, we will consider this is 0 because we have seen in the previous case when we use 0 it is easier to solve in the well, and then we will see what happens outside the well because of the extra potential. The potential can be outside also, the wave can be outside also. So we have to again solve the Schrodinger's time independent equation, and then we will get again different cases, and we will discuss in the next lecture. So I will just recap this again. So this is infinite well. In infinite well the potential outside is always infinity and potential inside is 0. In finite well there is some finite width or finite height of the well. We will assume this as u or v naught. Here the height is infinity but the width is fixed, 2a, or we can call as L. Similarly here also we will assume the width will be L, and we will see in the next lectures how to solve this. So these are different names for the wells. So rigid wall means infinite well, impenetrable also means infinite well. Here it is finite wall or finite well, so the wall is penetrable. Okay, then we have to use the Schrodinger's wave equation, time independent equation. Because of inside the potential is 0, this part becomes 0 and we get this only solvable equation, differential equation, and we know the general solution of this is a sin kx plus b cos kx. So this is oscillatory function. Okay, sin and cos both are oscillatory functions. So there is oscillatory function inside the well, and the same way we are getting the differential equation. So by comparison of these two equations we are considering k is equal to under root 2me upon h cross, or this is k square, 2me upon h cross square. And then using the same general solution we can use two different ways to solve this. One is asymmetric way. We consider 0 to a, 2a is the distance, and in this case what we use the boundary condition at x equal to 0 psi becomes 0, and at x equal to 2a the psi becomes 0. Okay, so from this we get b is equal to 0 and sine kx is equal to 0, or sine k to a is equal to 0. So from this sine n pi is 0, so we compare this two, and then from this we get k, and k is related to energy we have defined in earlier page. So from that we find out the value of energy. Okay, and again the similar way we apply the conditions. So here at minus a and at plus a the wave function is equal to 0. So implying the boundary conditions on the wave function, we get these two functions, or the two conditions. A and b cannot be simultaneously 0, because if they are 0 then total wave function is 0 everywhere. There is no space dependence, x चा काही गरजच नाही. Therefore this cannot be 0 simultaneously. So what can be the case? If b is equal to 0, then sin ka must be equal to 0, or if a is equal to 0, then cos ka must be equal to 0. So by using this method we have solved this. Again we will get two solutions. One is even solution, one is odd solution. For even solution n is odd, and for odd solution n is even. You just remember these things. You get the same equation. I missed somewhere here too. I don't remember where I missed 2, but here also you get the here you get 2 and here you get 4 because of the squaring. So you again get the same energy eigenvalue, and then we draw the wave functions. This is first wave function, this is second wave, third. So n equal to 1, 2, 3, and en will become e1, e2, e3. Okay, so you just put the value of n in this n, and you will get the value of n. So this is squared, n square. Energy is related to the square of n. All other terms are constant. So in the diagram also you can see, if this is 1 unit, then this is 4 unit because 2 square. Then this is 3 units, so 3 square. So if this is 1, this is 4, 9, 16, and so on. So the energy gap is going to increase. Okay, so this is the unique feature of square well. In finite well also this will be the same. The distance of energies or energy gaps is going to increase. So this is a very unique feature of square well, whether it is finite or infinite. From this solution we can get that energy is not continuous. Energy has some fixed values. Okay, energy is not random. Okay, so if this is energy unit, so in this energy unit only 1, 4, 9, okay, 16, these values are only possible, right? 2 times this unit is also not possible, 3 times this unit is not possible, or 2.5, 3.1, these are also not possible. Only certain energy units or certain energy values are allowed. They are also only possible values. All values are not possible. Therefore this type of problems in quantum mechanics are called as a discrete. So quanta is related to the discrete nature of particle. So what is discrete, what is quanta, why it is discrete? The discrete is energy. Wave function is continuous but energy is discrete. Okay, therefore you can see the gap. Wave function, here the wave function is continuous, here the wave function is continuous, but the energy in between two, there is no continuity, there is gap. From first to second level there is gap, from second to third there is a gap, from third to fourth there will be gap. So because of this gap we call this is a discrete nature. Therefore the word quantum is used for this mechanics. Okay, so it is related to the discreteness. So what is discrete? Energy is discrete but wave function is continuous. Okay.